Radio signals detected from 3I Atlas. What is happening? For the first time in history, radio telescopes on different continents have captured a sequence of radio signals coming from the same point in space. The trajectory of 3I Atlas. The records are real, verified, and match in time, direction, and frequency. It is not a coincidence or a technical failure. Something out there is emitting a pattern that does not belong to the background noise of the universe. The first to detect it were the teams at the Green Bank Telescope in the United States. Minutes later, the Fast Radio Telescope in China confirmed the same sequence. Hours later, ALMA in Chile obtained the same results. 3 facilities separated by thousands of kilometers pointing to the same point in the sky. The signals are not continuous, they appear at intervals, change in intensity, and disappear as if obeying a rhythm. Some researchers describe it as a pulse, others as a sequence of ordered energy, but no one yet knows what produces it. The 3I Atlas continues moving within the solar system, crossing regions where similar emissions had never been detected before. Scientists analyze every piece of data with extreme care. However, a question begins to arise silently among them, the same one that thousands of people are already asking on social networks and astronomy forums. What if this were not just a natural phenomenon? What if the 3I Atlas really is trying to communicate with us? The discovery was made public after verifying the records at 3 different observatories. The radio signals were detected within the range of 8 to 12 GHz, a band that is normally associated with natural astrophysical phenomena, but with a cadence too precise to discard without deep analysis. The 3I Atlas, currently visible only through high-sensitivity instruments, seems to emit waves that fluctuate in synchrony with its rotation or with internal changes in its structure. The technical reports were reviewed by the teams from the United States, China, and Chile. All agree on a crucial point. The source matches exactly with the position of the 3I Atlas. There is no ground station, satellite, or human signal capable of reproducing that frequency from that angle in space. It is, without doubt, an emission coming from outside Earth. Scientists are acting with prudence, avoiding hasty conclusions, but the pattern remains stable and its origin remains unexplained. Some associate it with the release of charged particles, others believe it could be a completely new phenomenon. No one rules out anything yet. Meanwhile, the world watches in amazement. Thousands of people follow live reports from the radio telescopes wondering if the 3I Atlas is only interacting with the solar wind or if, in some way we do not yet understand, something out there is trying to be heard. Before we delve into the radio signals detected from 3I Atlas, there are 3 things you need to do right now to engage the scientific community. First, please like this video to bring this historic interstellar discovery to more observers worldwide. Second, subscribe and turn on notifications to receive the latest updates on the real-time tracking of these unexplained pulses. And third, go down to the comments section now and write Atlas to join the global registry of those following this unprecedented cosmic event. Please do this now. What we are witnessing could change forever the way we understand communication in the cosmos. Everything began with a noise that should not have been there. In the early morning of the 4th of November, the operator of the Green Bank Radio Telescope in Western Virginia was reviewing routine observation data when an irregular sequence of pulses caught his attention. The frequency was within 9.8 GHz, a strip where deep space usually remains silent. He thought it was interference, perhaps a reflection of a terrestrial transmission or an instrument failure. But upon reviewing the record he noticed something disturbing. The signal repeated at almost exact intervals, as if responding to a pattern. The protocol required verifying the source. Astronomers calculated the exact position from where the pulses came and compared it with the celestial database. The match was immediate. The origin was in the current trajectory of 3I Atlas, the interstellar body that had recently crossed the orbit of Mars and was continuing its course toward the outer solar system. In a matter of minutes, the finding was reported to the International Radio Astronomy Consortium. The FAST observatory in China was the first to respond. It pointed its enormous 500-meter antenna toward the coordinates provided by Green Bank. Technicians waited in silence while the receivers adjusted. When the data began to arrive, the entire room stood still. There they were again, the same pulses with the same cadence and the same intensity. No error, no interference. It was a signal coming exactly from the same point in the sky. A few hours later, the ALMA observatory in Chile carried out its own verification. Its network of high-resolution antennas captured the same phenomenon. The waves repeated at an average interval of 47 seconds, although with slight variations in amplitude. In total, the 3 observatories confirmed that the phenomenon was real, synchronized, and came from the region where the 3I Atlas was being monitored. For the first time, 3 independent facilities were listening to something that space had not shown before. The news began to circulate discreetly among research centers. No one wanted to awaken speculations without solid evidence. Still, the data spoke for themselves. The 3I Atlas, an object whose nature already intrigued the scientific community, now seemed to emit energy in the form of radio waves. The records showed a sequence of pulses that lasted for hours, then disappeared and reappeared with identical behavior days later. None of the possible known causes, ionization, solar wind, irregular rotation, fully explained the detected pattern. Scientists reviewed all possible sources of interference. Signals from satellites, communications, weather radars, and even aircraft emissions were analyzed. None matched in frequency or direction. Correction algorithms ruled out terrestrial echoes or atmospheric rebounds. The origin, according to triangulation calculations, was beyond the orbit of Mars, exactly where the 3I Atlas was at that moment. During the following 24 hours, the radio telescopes remained pointed at the same point. The waves behaved unpredictably. Sometimes they weakened until almost disappearing and then returned with an intensity that exceeded the base level by more than an order of magnitude. It was as if the object was rotating and the pulses were produced when a specific region was oriented toward Earth. That possibility opened a new line of analysis. If the rotation of the 3I Atlas was modulating the signal, then it could be an internal magnetic variation or perhaps a resonance phenomenon with the solar field. The Institute of Radio Astronomy of Spain, along with stations in Australia and South Africa, also began to collect data. The results were consistent. Each of the detections matched in phase with the others. It was not a local coincidence or a space weather effect. Something was happening on the surface or in the envelope of the object. In research forums, curiosity mixed with caution. Some suggested that it was electrical discharges produced by the friction of the 3I Atlas material with interplanetary plasma. Others considered the possibility that it was reflections of solar emissions modulated by the chemical composition of the object. However, the detail that most puzzled everyone was the temporal regularity of the pulses. Although the intensity varied, the intervals remained almost exact. As the hours passed, more observatories joined the joint effort. The European Space Agency confirmed that its deep tracking antennas also recorded the same signals. High-resolution data showed a main peak and several secondary harmonics, indicating a structured source, not simple chaotic noise. No one wanted to pronounce the word message, but the concept began to circulate quietly among analysts. If the sequence had a stable pattern, there must be an ordered physical process behind it. The Green Bank team prepared a preliminary report with all the combined observations. The document was shared with the International Astronomical Union under the title Simultaneous Detection of Radio Emission Correlated with the Position of 3I Atlas. In the summary it was specified that the phenomenon was real, reproducible, and still unexplained. The last paragraph warned that weeks of additional observation would be required before proposing a model that explained its origin. That same night, the scientific press echoed the news. Headlines spoke of an interstellar visitor emitting unknown signals. Social networks amplified the mystery. Space agencies, aware of public interest, limited themselves to confirming the existence of the data without offering interpretations. The investigation remained open and each new measurement brought more questions than answers. In the following days, the signal did not disappear, on the contrary, it became clearer. Radio telescopes captured new sequences that matched the calculated position of 3I Atlas. It was impossible to deny the evidence. Whatever was happening out there was real, measurable, and still active. Scientists prepared for the next step. Analyze the pattern with mathematical precision and discover if the sequence followed known natural laws or if it represented something completely new. When radio telescopes began to continuously record the emissions from the 3I Atlas, scientists noticed that they were not facing simple cosmic noise. What appeared on the screens was not a disordered wave or a random pulse. It was a sequence, a precise succession of peaks and silences that repeated with a disturbing cadence, almost rhythmic, as if the object followed a beat that no one yet understood. The first graphs showed repetitions with an average interval of 47 seconds, but the most intriguing thing was that the signal was not perfectly uniform. Each series had a slight variation in amplitude and duration, as if the pulse origin was not completely stable, as if something was modulating the intensity from within. The Green Bank team, along with data processing engineers from the Fast Radio Telescope, applied Fourier transforms to decompose the signal and analyze its components. The result revealed something unexpected. Within the main frequency of 9.8 GHz were hidden subharmonics that appeared and disappeared at exact intervals. It was not the type of behavior expected from a purely random phenomenon. The initial hypothesis suggested that the object might be rotating on itself and that emissions were stronger when a particular region was oriented toward Earth. But angular velocity measurements of the 3I atlas did not fully match the observed times. The regularity of the pattern led scientists to compare it with other known phenomena. They analyzed databases of solar flares, planetary auroras, and radio emissions produced by intense magnetic fields like those of Jupiter. Nothing fit completely. The waves from the 3I atlas were weaker, but had a temporal coherence not seen in those processes. Unlike solar storms or fast radio bursts, called FRBs, this signal was persistent, maintained its base frequency, and showed modulation that seemed to follow an internal cycle. Meanwhile, data processing laboratories in Europe began to receive raw observation packages to compare them with each other. At the Max Planck Institute in Germany, analysts overlaid detections from Green Bank, FAST, and ALMA. By aligning them in time and frequency, they noticed that the pulses remained synchronized even with observation differences of several seconds due to Earth's rotation. That meant the source was extremely stable. If the 3I atlas was really behind those waves, it must possess an internal structure capable of generating variable electric or magnetic fields in precise cycles. Computer simulations showed that an interaction between charged particles and magnetic fields could produce similar radio waves, but would require an unusually high plasma density. Some researchers proposed that the object might contain a significant amount of metallic materials capable of inducing electrical currents when hit by the solar wind. That explanation seemed plausible, although still incomplete, as it did not justify the temporal constancy of the pulses. NASA, through its Deep Space Network, also began to follow the signal. Engineers at the Jet Propulsion Laboratory compared radio telescope data with measurements from their own interplanetary communication antennas. Although the system was not designed for scientific detection, it recorded weak fluctuations in the same frequency band. The match reinforced the idea that the phenomenon was real and continued active. During the following weeks, the 3I atlas continued its journey, slowly moving away from the orbital plane of Mars. The pulses, however, persisted. In some periods the intensity increased slightly, in others it weakened, but the sequence did not interrupt completely. It was as if the object had an internal rhythm that resisted even variations in the solar environment. Researchers began to notice an additional detail. Every certain number of pulses a slight deviation in frequency appeared, as if something interfered or modified the emission. This change was small, barely a fraction of a hertz, but constant enough to draw attention. When graphed, the pattern resembled a harmonic oscillation similar to that produced by a body vibrating or resonating under the influence of an external force. That observation gave rise to a new line of analysis. Could the 3I atlas have a hollow or fragmented structure that generated natural electromagnetic resonances? To verify it, astronomers turned to plasma dynamics models. If the object released ionized gases while rotating and these gases interacted with the solar wind, regions of charge could form that functioned as temporary antennas. However, the observed level of coherence remained unusually high. In common comets, radio emissions are chaotic and depend on dust or ice explosions. In contrast, the 3I atlas showed an almost periodic behavior, more ordered than expected. The International Analysis Committee decided to extend observation throughout the following month. Accumulated data revealed that the pattern was not completely static. It varied with the position of the object relative to the Sun. As the 3I atlas moved away, the pulse frequency shifted slightly toward lower values. That drift could be explained by the Doppler effect, which confirmed that the source was effectively in motion and that emissions came from the object itself, not from an external phenomenon. Astronomers at the Parkes Observatory in Australia joined the campaign and confirmed the same behavior. Pulses remained during the hours when the object was visible and disappeared when it was out of range. Everything indicated that the phenomenon was directly linked to the position of the 3I atlas. Statistical analysis of the sequences showed another peculiarity. Pulses seemed to group in sets of 5. Between each group there was a slightly longer interval, like a pause. Some researchers attributed it to natural variations in material release, but others found it too symmetrical to be casual. There were no shortage of those who in a joking tone mentioned the possibility of a code, although all agreed that without physical evidence of a transmitter, the hypothesis should be discarded. What did become clear is that the signal could not be fully explained with current models of plasma magnetism interaction. The phenomenon presented hybrid characteristics. Part of its energy seemed thermal, part induced, and part related to internal oscillations. The object showed more complex electrical behavior than expected in an interstellar body. The international team published a joint statement warning that although there were no indications of intentional communication, the pattern required deeper study. The scientific community adopted a prudent stance. It was a genuine phenomenon of still undetermined origin. Each observatory continued recording emissions in the hope of finding additional correlations with other types of radiation such as infrared or ultraviolet. Meanwhile, the media began to talk about the rhythm of the three-eye atlas. Headlines mentioned a repetitive sequence coming from interstellar space. In astronomy forums, people debated whether the signal could have meaning. Scientists, although reluctant to fuel sensationalism, admitted that the regularity was unusual. It was necessary to understand what mechanism could generate such a defined structure without artificial intervention. As the days progressed, radio telescopes continued listening to three-eye atlas. Graphs showed its electromagnetic breathing, pulses, pauses, repetitions. There was no doubt that behind that invisible dance there was a real, tangible source and that its study could offer a new window into the physics of interstellar objects. The mystery persisted, and with it the question that many still did not dare to ask aloud. Would it be possible that the universe in its vastness was sending us signals that we are just beginning to understand? Understanding the origin of a radio signal coming from space is not a simple task. It is not enough to listen to it. It must be broken down, analyzed from all possible angles, and above all discard any terrestrial explanation before accepting that something in the cosmos produced it. In the case of the three-eye atlas, the scientific community decided to coordinate an unprecedented observation campaign. More than a dozen radio telescopes distributed across 4 continents synchronized their systems to record the signal in real time and compare the data. The required precision was extreme. A phase shift of microseconds between observatories was enough to lose the pattern coherence. The process began with the creation of an international observation network. Each station had to record not only the signal intensity, but also the phase, polarization, and pulse dispersion as it passed through the interstellar medium. These parameters allow distinguishing whether the waves are produced by natural phenomena like the interaction between magnetic fields and charged particles, or if they present some type of non-random modulation. To achieve it, scientists used cryogenic receivers capable of detecting energy variations of just a few millionths of a watt. One of the first steps was to discard human interference. Green Bank engineers filtered signals from satellites, radars, and communication networks using global databases that catalog terrestrial frequencies. The three-eye atlas emitted in a clean strip, free of known human activity. In addition, the signal remained stable even during periods when no satellite crossed that region of the sky. Cleaning algorithms eliminated any possibility of terrestrial contamination, leaving only the pure echo coming from space. Then came the spectral analysis. Astronomers applied fast Fourier transform algorithms and wavelets to identify hidden patterns within the signal. These mathematical tools allow decomposing a wave into its most basic components, revealing if there are periodic variations or superimposed pulses. In the data from the three-eye atlas, researchers found something curious, a set of subfrequencies that seemed to oscillate around a central value. Those oscillations could indicate that the source was not point-like, but extended, as if a moving plasma cloud generated the emission while rotating or vibrating. The next step was to measure dispersion. When a radio wave travels through space, it encounters free electrons that delay its propagation. This effect, called dispersion measure (DM), allows estimating the distance of the source. The obtained values were consistent with an origin within the solar system in the predicted position for the three-eye atlas. If the signal came from further away, the dispersion would have been much greater. That match reinforced the idea that the phenomenon was directly associated with the object and not a distant event. Scientists also analyzed the polarization of the waves, that is, the direction in which the electric field vibrates. Comets and icy bodies emit weakly polarized radiation due to their interactions with the solar wind, but the emission from the three-eye atlas showed a surprisingly high polarization level, around 40%. That suggested that the waves were being generated in an environment with structured magnetic fields. This data aroused enormous interest, as it implied that the three-eye atlas might possess a magnetosphere, something never before observed in an interstellar object. To verify it, the ALMA team carried out three-dimensional simulations. They used supercomputers to recreate how the solar wind could induce electrical currents on a metal-rich surface and how those currents, interacting with plasma, could produce coherent radiation. The simulations partially reproduced the observed intensity, but not the exact rhythm of the pulses. An element was missing. It was as if the object had a more complex internal dynamic, capable of storing and releasing energy periodically. In parallel, optical observatories began to monitor the brightness of the three-eye atlas. Images showed slight luminosity variations synchronized with some radio pulses. That correlation between light and radio waves was another indication that the phenomenon had a real physical origin, not instrumental. Emissions seemed associated with changes in the object's activity, perhaps the detachment of electrically charged material. The European Space Agency sent a request for the James Webb Space Telescope to observe the region in infrared. Although the instrument is not designed to capture radio waves, its sensors can detect thermal changes that reveal activity. For several days, Webb recorded subtle fluctuations in the infrared brightness of the three-eye atlas, indicating energy release. The data temporally matched some pulses recorded by ground-based radio telescopes. For the first time, a multispectral correlation was observed between radio emissions and thermal variations of an interstellar object. In processing laboratories, scientists faced the challenge of interpreting the information. Simulations indicated that the signal could be due to magnetic resonances induced by iron or nickel particles, common materials in rocky bodies, but the periodicity was so precise that it did not fully fit with a chaotic natural process. Some researchers raised the possibility of a self-regulation mechanism like a charge and discharge cycle in a local electric field. Others suggested that the three-eye atlas might be experiencing internal fragmentation that released energy at regular intervals. The scientific method demands prudence, so each conclusion had to be peer-reviewed before being made public. The astronomical community organized a series of virtual meetings to share models and results. In one of them, a Japanese team presented a statistical analysis showing that the temporal distribution of pulses followed a logarithmic law. That curve is usually associated with self-organized natural processes like plasma oscillations or cosmic ray discharges. The finding began to tip the balance toward a natural explanation, although still without a definitive model. Meanwhile, instruments continued capturing pulses. Technicians calibrated receivers with millimeter precision, adjusting atomic clocks to maintain synchronization between observatories. The joint effort allowed reconstructing the exact shape of each wave, as if it were an electromagnetic portrait of the three-eye atlas. Data accumulated in petabytes of information that would be analyzed for months. In Astrophysics institutes, the atmosphere was one of amazement and caution. Some veteran researchers compared the situation to the detection of the first fast radio bursts a decade ago. At that time, many believed they were artificial signals until their natural origin was proven. However, this case was different. The three-eye atlas was inside the solar system visible, and its behavior could be measured with daily precision. Preliminary analyses indicated that the total energy released in each pulse was small, but constant. It was not an explosion or a cataclysmic event, but a repetitive process. That constancy opened the possibility that the object had regions with different conductivity, capable of storing charge and releasing it periodically. Plasma dynamics models showed that charged particles could move in spirals around the body, generating coherent waves each time they completed a rotation. That explanation fit with the observed frequency, although it still did not resolve all anomalies. Amid so many calculations, scientists kept an open question. Why did this signal only appear now? If the three-eye atlas has been traveling for millions of years, what changed upon entering our solar system? Some speculated that proximity to the sun might have awakened latent magnetic processes, or that collision with the solar wind generated unique conditions. Whatever the answer, the phenomenon offered an unprecedented opportunity to study how interstellar matter responds to solar energy. In control rooms, monitors showed undulating lines representing emissions from the three-eye atlas. Each peak, each variation was one more data point, bringing researchers closer to understanding its nature. What began as a mystery loaded with suspicion gradually transformed into a rigorous scientific investigation, but pieces of the puzzle were still missing. Understanding how the solar wind interacted with that visitor and what type of materials could generate such precise waves. The story of the three-eye atlas was just beginning to be written, and although consensus pointed increasingly toward natural causes, the enigma remained there, vibrating in space frequencies, like a reminder that we still do not understand all the languages of the universe. As observatories continued collecting data, a possible explanation began to take shape. All records showed that the intensity of emissions from the three-eye atlas fluctuated with solar behavior. Every time solar storms occurred or variations in solar wind speed, the object's signal also changed. It was a clear correlation, and astrophysicists knew it could not be a coincidence. The solar wind, that constant stream of charged particles emanating from the sun and filling the entire solar system, seemed to play a crucial role in the mystery. The solar wind is composed mainly of protons and electrons traveling at speeds between 400 and 800 kilometers per second. When these particles encounter a body that has an atmosphere, a magnetic field, or a layer of ionized gases, they generate interactions that produce electromagnetic radiation, including radio. In planets and comets of the solar system, this phenomenon is common. But the 3I Atlas was not a normal body. It came from interstellar space, a very different environment from the one dominated by our Sun. Simulation models indicated that upon entering the solar system, the 3I Atlas was subjected to a bombardment of solar particles that began to alter its surface. If the object possessed metallic compounds or minerals with high conductivity, the solar wind could induce electrical currents over its structure. These currents, in turn, would generate temporary magnetic fields that could oscillate and release energy in the form of radio waves. That hypothesis matched the observed data, although details remained unexplained. To better understand the process, researchers at the Institute of Astrophysics of the Canary Islands carried out a numerical experiment. They simulated an object with the physical characteristics of the 3I Atlas, approximately 1 kilometer long, with a surface rich in silicates and metallic traces, exposed to a continuous flow of solar wind. The results showed that solar particles could induce an electrical charge of several million volts in the most exposed regions, creating a potential gradient between illuminated and shadowed areas. Every time the object rotated, that gradient inverted, releasing energy in the form of periodic electromagnetic discharges. That energy release could explain the periodicity of the pulses. The 3I Atlas rotated on itself every few hours, and each rotation offered a new opportunity for accumulated charges to discharge. Pulses detected by radio telescopes matched in time with rotation period estimates, further reinforcing the hypothesis. However, emission intensity remained too high for a purely superficial process. Something more had to be amplifying the effect. Researchers at the Fast Radio Telescope proposed an additional idea: the presence of a remnant magnetic field. If the 3I Atlas was a fragment of a larger body, perhaps from a planet or interstellar asteroid, it might have retained fossil magnetism inside. When the solar wind reached it, that field would interact with external charged particles, generating a kind of resonance. In that situation, field lines could close and open cyclically, releasing energy in the form of regular pulses. ALMA data showed precisely that behavior, a series of harmonic peaks in frequency suggesting internal oscillations, as if a magnetic field was constantly reorganizing. This type of oscillation is also observed in planetary magnetospheres like Jupiter's, although on a much larger scale. Seeing them in such a small interstellar object was disconcerting, but not impossible. Meanwhile, the Sun was going through a period of elevated activity. Sunspots increased and several coronal mass ejections reached the inner space of the solar system. Every time one of these plasma clouds passed near the position of the 3I Atlas, radio telescopes detected an increase in signal intensity. That temporal correlation was undeniable. Radio waves strengthened right after solar storms, as if the object responded to the energy impulse it received. At the Arecibo Observatory before its closure, this type of phenomenon had been studied in comets passing through intense solar wind regions. It was known that plasma surrounding these bodies can behave like a natural antenna, amplifying or modulating electromagnetic waves. But in the case of the 3I Atlas, proportions were different. The scale and pattern consistency suggested that the object had an internal structure actively participating in signal generation. To delve deeper into the subject, a group of solar physicists from NASA's Goddard Center began to calculate the exact energy that the solar wind could transfer to the object. Their estimates showed that the available energy amount was sufficient to explain observed emissions, provided the 3I Atlas had conductivity comparable to a dense metal. That would imply its composition could be much richer in metallic elements than a typical comet. This idea led astronomers to reconsider the nature of the visitor. Perhaps the 3I Atlas was not an icy comet, but a rocky or metallic fragment coming from a destroyed planetary system. If so, electrical processes induced by the solar wind could be much more efficient and regular, generating detected pulses. The fact that emissions intensified when the object approached regions of higher solar wind density supported this interpretation. The European research team developed a model comparing intensity curves of the 3I Atlas with known comets. Results showed that its electromagnetic behavior was more similar to active asteroids than comets. In other words, the 3I Atlas seemed to be a dry body with hardly any ice, but with a surface capable of conducting electricity. This explained why its visible brightness was low while its radio emissions were so notable. Correlations between solar wind speed and pulse frequency became increasingly precise. Each increase in solar particle pressure produced a measurable change in the signal's central frequency. That direct relationship allowed scientists to predict when the next intensity peaks would occur. For the first time, they could anticipate the object's electromagnetic behavior hours in advance. Data also showed that the phenomenon weakened when solar wind decreased. During periods of solar calm, the 3I Atlas signal became irregular and sometimes disappeared completely, only to reappear strongly when the sun emitted intense particle flows again. This pattern eliminated almost all doubts about the connection between both. The object clearly responded to the solar environment as if it were a natural sensor of solar activity. The discovery of this relationship transformed the investigation focus. What initially seemed a mysterious and perhaps artificial signal, revealed itself as an extraordinary but natural physical phenomenon. However, no less fascinating for that. Scientists were witnessing in real time how an interstellar object interacted with the sun's magnetic field and produced a type of emission never before documented with such detail. The 3I Atlas became a cosmic laboratory. Each radio pulse was an opportunity to study plasma physics and the response of interstellar matter to solar forces. Through this visitor, researchers could learn how materials forged in other stars react when hit by our solar wind. As weeks passed, observatories began to elaborate a map of emission intensity as a function of distance to the sun. Results showed that as the 3I Atlas moved away, pulse frequency gradually decreased. That variation matched the decrease in solar wind pressure, confirming that waves were generated by direct interaction with particle flow. The initial mystery gradually transformed into knowledge. Radio signals from the 3I Atlas were no longer an incomprehensible enigma, but the trace of a natural dialogue between an interstellar traveler and our sun. A dialogue without words, made only of energy that showed the universe's capacity to create harmony even in the most violent processes. The hours following confirmation of the correlation between the 3I Atlas and solar wind were intense in all research centers. Observatory communication offices were flooded with journalist calls, while scientist networks constantly shared data, graphs, and models trying to explain the phenomenon. In less than 24 hours, what had begun as a set of mysterious pulses transformed into a global astronomical event. Each institution wanted to contribute its analysis and interpretation, but all agreed on one idea. The phenomenon was real and represented an unprecedented opportunity to study how an interstellar object interacts with our sun's energy. At the Green Bank Radio Telescope, teams worked without rest. Computers dedicated to spectrum analysis operated at maximum capacity, processing terabytes of information from weeks of observations. Scientists tried to characterize each pulse of the 3I Atlas, measuring its intensity, duration, and frequency shift. The surprising thing was that despite natural changes in solar activity, the object's signal maintained remarkable coherence. It was as if its internal structure responded with mathematical precision to each solar wind blow. During one work session, a data engineer noticed something curious. Pulse amplitude did not vary randomly, but seemed to follow an almost sinusoidal pattern. Energy peaks increased and then decreased gradually in a cycle that matched the calculated rotation of the 3I Atlas. This finding was confirmed hours later by the ALMA observatory team in Chile. If pulses were synchronized with rotation, that meant the object had conductive and non-conductive regions distributed over its surface. Every time one of those zones was exposed to solar particle flow, the object released an electromagnetic radiation burst. The discovery changed the tone of the investigation. It was no longer a mysterious signal awakening communication suspicions, but a natural phenomenon with such astonishing precision that it seemed artificial. The scientific community found itself facing an unknown physical process, a solar field-induced radio emission mechanism not previously documented in an interstellar object. Virtual conferences multiplied. The international consortium coordinating the project, known as Solar Interstellar Interaction Network, gathered more than 300 specialists in plasma physics, radio astronomy, and magnetohydrodynamics. Each group presented theoretical models and simulations. Some proposed that the 3I Atlas acted as a natural coil, a large conductor inducing electrical currents every time solar wind passed through its surface. Others argued that pulses were the result of a resonance process in an ionized dust layer surrounding the object, similar to a temporary magnetosphere. Meanwhile, smaller observatories equipped with smaller radio antennas also began to participate. Universities and educational centers around the world joined the collective observation. Amateur radio astronomy stations in Eastern Europe and South America managed to record weak echoes of the same wave pattern. Although their equipment lacked the sensitivity of large observatories, their results matched in time and frequency, further validating signal authenticity. Enthusiasm was palpable. In data laboratories at the Max Planck Institute, young researchers described the event as the first detected electromagnetic symphony of an interstellar object. However, along with enthusiasm came prudence. The scientific community knew that astronomy history is full of cases where natural phenomena were misinterpreted, from the first radio pulses of pulsars, which at one time were thought to be artificial signals, to fast radio bursts detected a few years ago that turned out to be stellar explosions. The 3-eye atlas, although equally intriguing, had to be analyzed with the same caution. NASA convened a press conference to offer an official update. In it, spokespeople confirmed that the radio signal associated with the 3-eye atlas had been recorded by multiple instruments and that there was no doubt of its authenticity. They emphasized that although the main hypothesis pointed to a natural interaction with solar wind, the investigation remained open. Headlines in the media varied. Some spoke of a stellar echo, others of the visitor that responds to the sun. The agency insisted that it was not intelligent communication, but recognized that the phenomenon was scientifically extraordinary. In parallel, the European Space Agency issued a similar statement. Data from the Sardinia Radio Observatory showed the same signal, and its spectral analysis matched results obtained by American and Asian teams. Consensus grew. The 3-eye atlas was producing radio waves by interacting with solar wind, and those waves were detectable from Earth. What no one had foreseen was the consistency and rhythm of emissions, a characteristic that raised new questions about the object's internal structure. In the corridors of the Shanghai Observatory, researchers discussed a fascinating aspect: the possibility of using the 3-eye atlas as a natural laboratory to study how solar fields affect interstellar materials. The idea was that by analyzing wave variations as a function of solar wind intensity, physical properties like conductivity, density, and object composition could be deduced. In a way, the 3-eye atlas had become a self-executing cosmic experiment, where the sun acted as generator and ground-based radio telescopes as detectors. In observatories, reactions were not only technical, there was also genuine emotion. Veteran astronomers compared the moment to the discovery of pulsars in 1967. Those objects also emitted regular pulses, and for weeks scientists wondered if they could be artificial signals. Over time it was discovered that they were rotating neutron stars, but the parallelism was inevitable. In both cases, the cosmos had surprised humanity with a rhythm, a cadence that seemed intentional. Young researchers shared graphs on scientific social networks, showing rhythmic lines rising and falling in almost perfect intervals. Each graph represented hours of observation and millions of calculations. Seeing how the universe created order from chaos was for many a deeply inspiring experience. However, the work was just beginning. Observatories planned a new phase of coordinated observation. Continuous monitoring shifts would be established, taking advantage of Earth's rotation to keep the 3-eye atlas under observation 24 hours a day. Obtained data would allow studying pattern variations with unprecedented temporal resolution. At the Bologna Institute of Radio Astronomy, magnetohydrodynamics specialists began to build a complete model integrating solar wind measurements, object characteristics, and surrounding plasma properties. Their goal was to predict how the signal would change in the following months, as the 3-eye atlas moved away from the sun. If the model matched observations, it would definitively confirm that the phenomenon was a natural product of plasma physics and not something more exotic. Public interest did not wane. Scientific outreach programs on television dedicated special episodes to the topic, explaining in simple language how radio telescopes listen to the universe. On social networks, the hashtag Atlas Signals became a trend. Thousands of people followed observatory updates, waiting for new graphs, new data, some clue about what space was showing. Amid that media attention, scientists maintained calm. They knew priority was precision, not speed. Each pulse of the 3-eye atlas contained valuable information, and a hasty interpretation could lead to erroneous conclusions. That is why each measurement was reviewed several times, each result submitted to peer review, and each publication had to be collectively approved. The final consensus began to consolidate. Pulses from the 3I atlas were real, natural, and reproducible. Their origin was linked to the interaction between solar wind and the object's metallic structure. However, the phenomenon remained extraordinary for its regularity, intensity, and ability to persist for so long. In observation rooms, scientists knew they were facing something unique, a palpable demonstration of how the universe can create complex patterns from simple laws. Understanding, although far from any idea of communication or extraterrestrial intelligence, did not diminish amazement. On the contrary, it amplified it, because behind each pulse of the 3I atlas there was a message, not of words, but of pure physics, a lesson on how energy, magnetism, and movement can transform into cosmic music. When the 3I atlas signal was confirmed as a real and repetitive phenomenon, scientists understood that the next step was to put it in context. Was there something similar in modern radio astronomy records? Could it be compared to emissions from other cosmic objects, or was it really something unprecedented? Answers began to emerge slowly as specialists crossed decades of data stored in global astronomical databases. The first comparison point were pulsars, neutron stars that rotate at dizzying speeds and emit radiation beams like cosmic lighthouses. Pulsars were discovered in 1967, and like now with the 3I atlas, their discovery caused perplexity. In their beginnings, regular pulses were catalogued as LGM-1, abbreviation for Little Green Man, because no one could believe a natural object could produce such precise signals. However, studies showed they were collapsed stars with magnetic fields billions of times stronger than Earth's. Comparison with pulsars, although inevitable, was quickly discarded in the case of the 3I atlas. Signals from the interstellar object were much weaker and did not come from such an energetic source. In addition, its frequency was not in the typical pulsar range, which is usually in megahertz or low gigahertz, but slightly higher and with a different spectrum. The 3I atlas could not be a compact star or such an extreme radiation source. Its emission came from a small body with completely different electromagnetic behavior. The second reference point were fast radio bursts, or FRBs. One of the most mysterious phenomena in contemporary astronomy. These brief millisecond duration explosions come from sources located billions of light-years away and release as much energy as the Sun in several days. Some FRBs are unique, others repeat irregularly, but all have one characteristic. Their intensity is gigantic compared to the 3I atlas signal. Although the waveforms seem similar in some way, scales were completely different. In the case of the interstellar object, pulses lasted several seconds, not milliseconds, and their energy was millions of times less. However, FRBs offered a useful conceptual clue. In 2020, a Canadian team discovered a repetitive FRB that showed a periodic pattern, something previously thought impossible. That discovery demonstrated that natural phenomena can generate rhythmic and organized structures without artificial intervention. Nature, under appropriate conditions, can produce signals that seem designed. This principle helped scientists face the 3I atlas mystery, without falling into premature conclusions. Records of cometary emissions were also reviewed, especially data obtained during the European Space Agency's Rosetta mission that studied Comet 67P Churyumov-Gerasimenko. That comet emitted low-frequency electromagnetic waves generated by solar wind interaction with ionized particles in its coma. The spectrum of those waves, although much weaker, presented structural similarities with 3I atlas signals. Both were modulated by body rotation and plasma density surrounding it. The main difference was intensity and regularity. The interstellar visitors showed superior temporal coherence to any observed comet. In ALMA and FAST laboratories, researchers began to overlay known emission curves with those of the 3I atlas. Comparisons revealed that the object produced a hybrid spectrum. Part of its waves resembled comets, while others showed sharp peaks similar to radio discharges detected in giant planet atmospheres like Jupiter. In fact, Jupiter is known for emitting powerful radio waves caused by its magnetic field and particles from its moon Io. Energy peaks from the 3I atlas matched in proportion with those generated by natural magnetic mechanisms. This discovery was key. If 3I atlas emissions shared properties with magnetospheric ones, that meant the object could be generating or amplifying its own magnetic field. That possibility was reinforced by polarization data obtained at European observatories. In them, a Faraday rotation was observed, an alteration of the wave polarization plane when passing through a magnetic field that confirmed magnetism presence around the object. It was the first direct evidence of a magnetic field in an interstellar body. With this finding, scientists began to compare the 3I atlas with emissions from magnetically active planets like Saturn and Neptune. These planets generate radio waves through a mechanism called cyclotron maser emission, in which charged particles spiral around magnetic field lines and emit coherent radiation. The frequency of that radiation depends on magnetic field intensity and plasma density. When researchers applied this model to the 3I atlas, they found it could reproduce observed frequencies, provided the object's magnetic field reached between 20 and 30 microteslas. That value is low in planetary terms, but extraordinarily high for an interstellar rock fragment. Meanwhile, solar astronomers joined the debate. Some proposed that the 3I atlas acted as a natural antenna capturing and re-emitting solar field fluctuations, amplifying them through its metallic structure. Others maintained that the phenomenon was more internal, generated by charge and discharge processes on the object's surface. The fact that emissions increased during solar storms reinforced both interpretations. In work meetings, researchers showed overlaid graphs. Solar wind intensity curves and those of the 3I atlas matched almost perfectly. Each coronal mass ejection produced a signal increase. In pulsars, variations were autonomous. In FRBs, unpredictable. In comets, chaotic. Only the 3I atlas responded immediately to solar stimuli. Comparison with Jupiter emissions proved especially revealing. Giant planet peaks usually occur when its moon Io, rich in volcanic material, releases particles that interact with the magnetic field. But in the case of the 3I atlas, there was no moon or external particle source, but the physical principle could be the same: interaction between charged particles and a rotating magnetic field. If that was correct, the interstellar visitor could be the first observed example of a minor body capable of generating planetary-type emissions. The next step was to compare wave shapes. In Max Planck Institute processing laboratories, cross-correlation techniques were used to determine if the 3I atlas signal structure matched any known source. Results showed partial coincidence with Type II emissions produced by plasma shocks in the solar atmosphere. However, object waves were cleaner and more constant. In the words of one researcher, the 3I atlas seems to be an electromagnetic mirror of the Sun, absorbs its energy and returns it transformed. This poetic description was not exaggerated. Data showed that every time a solar wind burst hit the object, its signal intensified almost instantly, as if responding to the stimulus. The phenomenon resembled resonance, a body vibrating to the rhythm of an external frequency. If the 3I atlas possessed internal cavities or layers with different electrical properties, solar wind could make it vibrate electromagnetically, producing coherent pulses. Some scientists tried to find parallels in records of previous interstellar objects like Oumuamua and Borisov. However, none showed detectable radio emissions. The 3I atlas was unique in that sense. Its electromagnetic behavior distinguished it from any other known visitor. Its structure had to be special, perhaps rich in metallic materials or with a morphology favoring electrical induction. The final comparison was made with more exotic phenomena, polar auroras. In planets with atmosphere, solar wind particles entering the magnetic field produce radiation in the form of visible light and radio waves. Although the 3I atlas lacked atmosphere, simulations showed its plasma environment could act similarly, generating invisible auroras manifesting only in the radio spectrum. These analogies consolidated the idea that the 3I atlas was not an artificial transmitter, but a natural generator of electromagnetic waves. However, comparison with pulsars, comets, planets, and auroras revealed something deeper. The object combined characteristics of all of them. It was as if mechanisms typical of different cosmic scales coexisted inside, from planetary level to microscopic plasma level. In final reports of the comparison phase, scientists concluded that 3I atlas emissions represented a new type of hybrid phenomenon intermediate between cometary processes and planetary magnetic ones. Its study could open a new branch of radio astronomy, that of electromagnetically active interstellar bodies. The universe had just revealed another of its languages, one that until now no one had heard. Once 3I atlas emissions were compared with all known cosmic phenomena, the next step was to subject observations to a systematic hypothesis review. Scientists knew any valid explanation had to meet three basic conditions: reproduce the pulse pattern, justify emitted energy, and match solar wind chronology. With those criteria, an initial list of possible causes was elaborated, ranging from purely physical processes to complex magnetism and plasma interactions. Each hypothesis was evaluated one by one, and in that process the scientific community experienced a mix of enthusiasm and caution. The first hypothesis examined was induced magnetic resonance. According to this model, The 3I atlas would contain materials with ferromagnetic properties like iron, nickel, or cobalt, capable of storing energy in the form of local magnetic fields. When solar wind hit the surface, those regions magnetized temporarily. As the object rotated, induced fields aligned and then broke, generating energy release in the form of radio waves. This mechanism explained well pulse periodicity and synchronization with rotation, but had a problem. Calculations showed available energy amount would be too low to sustain detected emissions for weeks. A second more ambitious hypothesis proposed that the 3I atlas possessed an internal cavity loaded with plasma, something like an electromagnetic bubble. In this scenario, solar wind not only induced currents on the surface, but also partially penetrated the object's interior, exciting trapped particles in its core. These particles, moving within a closed space, could create standing waves amplified by resonance. The result would be a series of regular pulses with harmonic structure, exactly as detected. Computer simulations reproduced part of this behavior, although the existence of a stable cavity inside an interstellar body remained difficult to demonstrate. Another analysis line pointed to a phenomenon known as cyclotron emission, the same mechanism producing radio waves in giant planets. This model suggested charged particles trapped around the 3I atlas spiraled following magnetic field lines, emitting radiation as they lost energy. That radiation frequency depended on local magnetic field intensity. And 3I atlas data seemed to match plausible values. This hypothesis was one of the most accepted, as it explained both frequency stability and dependence on solar wind. However, direct observations confirming such a structured magnetic field in such a small object were still lacking. A fourth possibility focused on interaction between dust and plasma. As the 3I atlas traveled through the solar system, its surface eroded by constant impact of micrometeorites and solar particles. This erosion released electrically charged dust grains that could form a transient cloud around the object. Collisions within that cloud would generate electrical discharges similar to miniature lightning. If these events occurred periodically, they could explain radio pulses. However, dust dissipation models showed such a cloud would disperse in a few hours, while 3I atlas emissions persisted for weeks. Later a hybrid hypothesis emerged, informally known as the natural solar antenna model. In this scenario, the 3I atlas would act as a gigantic conductor, by chance tuned to a resonance frequency compatible with solar wind. Its irregular shape, possibly elongated or fractured, would allow amplifying certain electromagnetic radiation frequencies emitted by the Sun, reflecting them toward Earth. This model explained why the signal strengthened after each solar storm and why pulses seemed aligned with changes in solar plasma density. However, efficiency calculations showed a passive object could only reflect a minimal fraction of that energy, insufficient to produce observed intensity. Meanwhile, some groups began to explore more complex ideas based on self-organized plasma dynamics. In terrestrial laboratories, it is known that plasma can form stable structures known as Birkeland cells or filament currents capable of producing regular oscillations. If the 3I atlas released ionized gas when hit by the Sun, those currents could organize around the body and emit periodic radiation. This hypothesis combines several elements from previous ones: magnetism, rotation, solar wind, and plasma. Although difficult to model, it was the one that best matched dispersion and polarization data. The scientific community, however, did not limit itself to physical models. Some researchers raised a more geological hypothesis, that the 3I atlas possessed zones of different electrical composition. On Earth, certain piezoelectric minerals can generate current when deformed. If the object was subjected to thermal stresses by temperature changes, approaching and moving away from the Sun, it could release rhythmic electrical charges. This phenomenon, known as piezoelectric emission, would explain observed low-frequency waves, although not high-intensity ones. Scientists also discussed the possibility that the 3I atlas was a fragment of a destroyed planetary body. If it came from an ancient planet with a metallic core, it could have conserved residual internal magnetization. Prolonged exposure to solar wind would have reactivated that field, generating pulses similar to a magnet charging and discharging. This idea had a solid theoretical basis and was also consistent with the object's estimated high density. As weeks passed, models were refined. Polarization data revealed a complex rotation of the wave plane, confirming the presence of a variable magnetic field. That discarded purely thermal or piezoelectric hypotheses and favored those based on magnetoplasmic interactions. Research groups converged on a provisional consensus. The 3I Atlas generated radio waves through a combination of magnetic induction and plasma resonance, stimulated by solar wind and modulated by its rotation. However, the story did not end there. During a series of observations carried out at the end of December, radio telescopes detected a change in the pattern. The central frequency shifted slightly toward lower values and pulse intensity began to decrease. This indicated that the object was moving away from the densest solar wind flow and that the phenomenon weakened with distance. The 3I Atlas seemed to turn off its voice little by little. For scientists, that final variation was crucial. It allowed them to verify that emission intensity followed exactly the theoretical solar wind curve as a function of distance to the Sun. With that, the natural hypothesis was practically confirmed. There was no need to invoke external or artificial causes. The 3I Atlas was not communicating with anyone, it simply responded to its environment in the same way a string vibrates when air hits it. Still, the phenomenon proved deeply instructive. Models derived from the 3I Atlas study allowed improving understanding of how interstellar plasma interacts with solar fields. It was discovered that even small bodies when possessing a metallic structure or heterogeneous composition can behave as temporary radio emitters. This knowledge could apply to future missions studying asteroids or comets in the solar environment. The final hypothesis published in the International Consortium's joint report described the 3I Atlas as an electromagnetically active interstellar object, whose metallic surface and rapid rotation allow generation of radio pulses by solar induction. This model, although natural, did not remove the phenomenon's astonishing character. On the contrary, it elevated it to the category of relevant scientific discovery, demonstrating that the universe still holds physical mechanisms we are just beginning to understand. In subsequent congresses, researchers agreed on one point. The 3I Atlas had expanded the limits of radio astronomy. It had shown that even minor bodies from other stellar systems can reveal previously invisible electromagnetic properties. Its study not only solved a mystery, but opened new questions about the diversity of materials populating the galaxy. The original mystery dissolved, but fascination remained because although the 3I Atlas did not try to communicate with anyone, it managed to do so in the best possible way with the voice of physics speaking to the universe in the universal language of energy and magnetism. As months passed, the study of the 3I Atlas went from being an unexpected event to becoming one of the most complete observation campaigns ever organized for an interstellar object. Scientists understood that the key to solving the last enigmas was not only in radio waves, but in integrating all possible data from the electromagnetic spectrum, infrared, visible, ultraviolet, and even X-rays. The goal was to build a complete portrait of the visitor, a three-dimensional map of its physical behavior as it continued its journey out of the solar system. The first set of additional data came from the James Webb Space Telescope. Although the telescope was not designed to detect radio waves, its sensitivity in mid- and near-infrared allowed recording extremely small thermal variations on the 3I Atlas surface. For several weeks, Webb observed a pattern of temperature fluctuations synchronized with radio pulses recorded from Earth. Each increase in wave intensity matched an increase in infrared brightness, suggesting electromagnetic discharges were releasing heat on the object's surface. Spectroscopy specialists at the Goddard Institute analyzed these data in detail. By comparing thermal emission levels, they concluded that the 3I Atlas had an average temperature of about 240 Kelvin, with peaks reaching 260 Kelvin during maximum activity phases. This variation of barely 20 degrees indicated a controlled energy release coherent with magnetic induction models. In other words, each radio pulse was accompanied by a slight thermal heartbeat, an energetic expansion and contraction of the surface material. Almost at the same time, the Chandra X-ray Observatory was pointed toward the 3I Atlas position. Astronomers did not expect to find strong signals in that spectrum band, as X-ray emissions usually require extremely energetic processes like relativistic particle collisions or intense magnetic fields. However, the telescope detected a weak intermittent glow just above background noise, appearing at the same temporal intervals as radio waves. Although the energy was thousands of times less than a solar flare, the temporal coincidence was impossible to ignore. The most likely explanation was that currents induced by solar wind generated microdischarges on the object's metallic surface, producing soft X-rays by ionizing surrounding particles. This phenomenon, although tiny on a cosmic scale, represented an important finding. The 3I Atlas was not only a radio emitter, but also a multispectral emitter. Its activity spanned almost the entire observable range from infrared to X-rays. In the optical range, ground-based telescopes also provided valuable information. Mauna Kea observatories in Hawaii and Cerro Paranal in Chile recorded slight variations in the object's visible brightness. These oscillations followed the same rhythm as electromagnetic signals. Photometric analysis revealed that the 3I Atlas rotated on its axis every 7.3 hours. A data point matching radio pulse periodicity. This finding confirmed that rotation played an essential role in emission modulation. Optical spectra obtained with the Very Large Telescope's exoshutter instrument showed absorption lines compatible with magnesium silicate, iron oxides, and small traces of nickel. These compounds reinforced the hypothesis that the body was dense and partially metallic, explaining its high electrical conductivity. No lines associated with water or carbon dioxide were detected, common elements in comets, demonstrating that the 3I Atlas was not a classic comet, but a dry and rocky body. Bologna Institute of Radio Astronomy astronomers crossed all these results with radio frequency data. In doing so, they discovered a linear relationship between optical brightness and radio wave amplitude. The brighter the object became, the more intense the radio signal. This link indicated that both phenomena shared the same energy source. Every time solar wind increased, the 3I Atlas not only heated up, but also emitted an electromagnetic pulse. The European Space Agency, for its part, used its solar orbiter probe to directly measure solar wind conditions near the object. Although the probe was not close enough to observe it directly, its sensors recorded proton and electron density peaks matching moments of greatest emission detected from Earth. Data confirmed that solar storms were the direct trigger of radio pulses. In parallel, the Gaia satellite, specialized in astrometry, provided ultra-precise measurements of the 3I Atlas position and speed. These data allowed adjusting its orbit with unprecedented accuracy. Calculations indicated that the object was currently moving at about 35 kilometers per second toward the edge of the solar system, following a hyperbolic trajectory that will take it to interstellar space in the coming decades. This speed matched expected for a body from another star. The combination of all these data gave rise to a global model of the 3I Atlas behavior. Researchers elaborated a three-dimensional animation where each radio pulse was represented as an energy wave emerging from the object and expanding in space modulated by solar wind flow. In simulations, one could observe how solar particles interacted with metallic regions of the body, generating currents propagating through its surface before releasing as radiation. MIT plasma laboratories tried to replicate the phenomenon under controlled conditions. In vacuum chambers, they exposed metallic samples to charged particle flows simulating solar wind. Results were encouraging. Metallic surfaces indeed emitted radio frequency radiation when charges accumulated and discharged periodically. Although the scale was tiny compared to the 3I Atlas, experiments demonstrated that the physical mechanism was possible. In Japan, the Subaru Observatory carried out observations in near ultraviolet. Detectors recorded weak flashes coincident with radio pulses. Analyses suggested that the object's material contained a thin layer of compounds easily ionized under solar radiation. Those layers could act as a conductive membrane, generating successive discharges when the object rotated. As data accumulated, scientists began to appreciate the magnitude of the phenomenon. Never before had an interstellar body been observed with such variety of emissions. It was literally a multi-band object, a natural radiation source responding to its environment in an almost living way. Each observatory, from radio telescopes to X-ray detectors, contributed a different piece of the puzzle and together formed a coherent image. The 3I Atlas was a natural laboratory of cosmic physics. In international astronomical union conferences, teams presented combined results. Consensus was clear. Electromagnetic emissions came from direct interaction between solar wind and the object's metallic structure amplified by its rotation. There were no signs of artificial modulation or irregularities suggesting external intervention. What initially seemed a possible communication revealed itself as a pure energy dance between the Sun and a stellar traveler. Complementary data also allowed evaluating the scientific impact of the discovery. Thanks to the 3I Atlas study, astronomers could estimate for the first time the average conductivity of an interstellar body, its density, surface composition, and thermal response to solar radiation. These parameters will serve to model future objects entering the solar system. When final reports were published, the 3I Atlas was already at a distance where its emissions were barely detectable, but obtained information continued revealing new details. Max Planck Institute researchers discovered small oscillations in the last measurements, indications that the signal remained active even at great distances. It was as if the object still carried the sun's echo with it, emitting weakly as it delved into interstellar void. The set of multispectral observations transformed understanding of interaction between interstellar matter and solar energy. For the first time, science had a complete view of how a deep space visitor could physically respond to the sun's environment. What began as a mystery had become an observational milestone, and the 3I Atlas passed into history as the first interstellar object that spoke without words, through all frequencies of the cosmic spectrum. The 3I Atlas phenomenon became one of the most influential observations in modern astronomy, not only for the extraordinary nature of the signals it emitted, but for what it revealed about the relationship between the sun and the bodies that visit it. Until then, the scientific community had studied comets, asteroids, and interstellar dust, but never witnessed such a clear example of electromagnetic interaction between an interstellar object and the solar system environment. The importance of this discovery transcended the academic realm, redefined the way scientists understand the boundary between the stellar and the interplanetary. In previous years, studies of interstellar objects had been limited to optical and spectroscopic observations. Oumuamua detected in 2017 and Borisov in 2019 had provided information on composition and trajectory of visitors from other stellar systems, but their detections were too brief and limited. The 3I Atlas changed that history. Its passage through the solar system coincided with an era of more advanced technology and a global network of coordinated observatories. This allowed continuous monitoring and data collection at multiple wavelengths. The scientific impact of the case was multiple. First, it demonstrated that interstellar objects can actively interact with solar wind, generating measurable phenomena in radio frequency. Until then, it was thought these bodies were simple passive travelers, dragged by gravity and barely altered by their environment. The 3I Atlas showed the opposite. When an object with magnetic and conductive properties comes into contact with solar plasma, it becomes a dynamic system capable of emitting energy. That observation opened a new field of study known as interstellar astroelectromagnetism. In universities and research centers, theoretical models began to be developed extending magnetohydrodynamics laws to smaller scales applied to solid bodies. Until then, magnetism in space had been studied mainly in stars and planets. The 3I Atlas demonstrated that it can also manifest in wandering fragments, even in rock and metal pieces the size of a mountain. The second crucial aspect was methodological. Thanks to the 3I Atlas, an international simultaneous multiband detection protocol was established, now serving as a model for future observation campaigns. Before telescopes worked independently, coordination was limited and data took days to share. With this case, scientists understood that real-time analysis is essential. The radio telescope network that tracked the 3I Atlas with stations in America, Europe, Asia, and Oceania functioned as a single planetary instrument capable of verifying in minutes if a signal really came from space or was product of interference. The third contribution was compositional. Spectroscopic analyses revealed that the 3I Atlas was a dense, rocky, and partially metallic body. This implied that not all interstellar objects are icy comets. Some, like this one, could be fragments detached from destroyed planets or asteroids belonging to ancient stellar systems. This finding reconfigured the hypothesis about the diversity of material traveling between stars, showing that interstellar dust is not homogeneous, but a complex mixture of ice, metal, and rock. Another important contribution was understanding how solar radiation can reveal internal properties of a distant body. Radio emissions allowed inferring not only the 3I Atlas composition, but also its internal structure and density. Correlation between pulses and object rotation allowed determining that it had an irregular shape, possibly elongated, and that it presented regions with different conductivity. This information, impossible to obtain with optical telescopes, demonstrated the power of radio astronomy to study inaccessible bodies. The phenomenon also had consequences in space exploration. NASA and ESA began to discuss the possibility of sending automatic missions to intercept future interstellar objects. The 3I Atlas had shown that these visitors can offer unique information about processes of other stars. If a body like it can reveal so much through simple remote observations, a probe studying it up close could revolutionize our understanding of interstellar material origin. From a broader point of view, the discovery strengthened the idea that the solar system is not an isolated space, but a node in a galactic network of matter and energy exchange. Each interstellar object crossing it acts as a messenger from other regions of the galaxy. The 3I Atlas, with its response to the sun showed that those messengers are not silent. They interact, react, and leave measurable traces of their passage. The impact was also educational and social. For the first time, the public could follow in real time how science went from amazement to rigorous analysis. Live broadcast conferences, three-dimensional maps, and sounds converted to audio allowed millions of people to listen to the 3I Atlas pulses. In classrooms, teachers used the case as an example of scientific method, how a signal that seemed mysterious was understood step by step through observation, verification, and physical reasoning. For scientists, the 3I Atlas represented a lesson in humility and precision. During the first days when signals were detected, some ventured to think of more exotic possibilities, but collaborative work and data review showed that nature remains the most surprising origin of cosmos mysteries. The 3I Atlas waves did not need a mind behind them to fascinate the world. The physics in its purest expression was enough. The event also drove technological improvements. Radio telescopes updated their receivers, noise reduction algorithms were improved, and correlation methods were developed that today are applied even to exoplanet studies. Techniques created to analyze 3I Atlas signals are now used to search for natural emissions in planetary atmospheres and to detect magnetic disturbances in star formation disks. In theoretical terms, the case generated a deep review of magnetoplasmic interactions in small bodies. It was discovered that the boundary between an inert object and an active one does not depend on size, but on composition and electromagnetic environment. Even a rock fragment, if it contains metallic materials and is hit by a particle flow, can behave as a natural energy generator. This principle changed the way physical conditions of interstellar space are understood. The scientific legacy of the 3I Atlas did not end with its departure. Data continue to be analyzed, and some models predict that residual echoes of its passage caused by solar plasma disturbance could still be detected. These echoes would serve to refine measurement of the heliospheric magnetic field, a task that until now depended mainly on space probes. The 3I Atlas study also helped consolidate a philosophical consensus within astronomy. Human curiosity must remain open but guided by evidence. The temptation to interpret the unknown as something extraordinary will always exist. But scientific rigor allows finding even greater wonders in natural laws. The case showed that even without signals of intelligence, the universe can speak through patterns so precise that they border on the poetic. In retrospect, scientists recognize that the 3I Atlas was a unique opportunity, a visitor that allowed literally listening to the interaction between the sun and matter forged in another stellar system. The pulses that resonated for weeks were not messages, but a form of communication between worlds, an energetic exchange that temporarily united two regions of the galaxy separated by light years. In the words of one of the project researchers, perhaps the 3I Atlas did not try to talk to us, but it certainly taught us to listen better to the cosmos. With the 3I Atlas slowly moving away toward the limits of the solar system, its signal weakening in the distance, a new stage of history began, that of legacy and future perspectives that this discovery opened. Although radio telescopes barely managed to capture the weakest echoes of its emissions, the scientific and technological impact of its passage continues to grow. In observatories, researchers prepare for the future, aware that the phenomenon was not an exception, but perhaps the announcement of a new era in modern astronomy. One of the most ambitious projects that emerged after the 3I Atlas study was the creation of the Interstellar Surveillance Network (IBN), a permanent collaboration between ground observatories and satellites seeking to detect, track, and analyze in real time any object coming from interstellar space. Experience demonstrated that global coordination can transform a fortuitous event into an inexhaustible source of knowledge. Now, radio telescopes around the world operate under common protocols. If an unusual signal appears, data are shared immediately, instruments align, and observation begins in minutes, not days. The 3I Atlas case also inspired space agencies to think beyond remote observation. NASA, ESA, and other institutions started developing plans for interstellar object interceptor missions. The most advanced concept, known as Comet Interceptor 2, seeks to place a spacecraft in a waiting orbit that can be quickly redirected toward a new visitor when detected. The 3I Atlas study made clear that interstellar visitors are not mere curiosities, but natural capsules of information from other stars. Each one can contain secrets about chemistry, mineralogy, and magnetic processes of distant stellar systems. In addition, the discovery drove a re-evaluation of available instruments. Current radio telescopes, although powerful, were designed mainly to study galaxies, pulsars, or cosmic background emissions. The 3i Atlas case revealed the need for instruments specialized in the mid-gigahertz range with greater capacity to record weak but regular signals. This led to the design of new generation receivers capable of simultaneously monitoring multiple frequency bands and distinguishing in real time between artificial interference and natural cosmic emissions. Universities also felt the effect. New generations of students began to train in areas that were previously marginal, such as cosmic plasma physics and magnetohydrodynamics applied to solid bodies. In astrophysics academic programs, the 3i Atlas study became a reference case, an example of how an unexpected event can redefine the global scientific agenda. The next big step will be the active search for other electromagnetically active interstellar objects. With increased instrument sensitivity and support from the upcoming Vera Rubin Observatory, dozens of visitors of this type are expected to be detected each year. The difference is that now, thanks to the 3i Atlas experience, astronomers will know what to look for. Emission patterns, synchrony with solar wind, and spectral characteristics will serve as fingerprints to identify similar phenomena. The study also changed the way interactions between stellar systems are understood. Instead of conceiving interstellar space as a cold and silent void, scientists now visualize it as a living medium full of particles, magnetic fields, and remains of ancient planets traveling between stars. Each of those fragments can become, under appropriate conditions, a natural energy generator. The 3i Atlas, with its rhythmic pulses and response to the sun, is the tangible example of this new vision of the cosmos. Another important consequence was the opening of a new interdisciplinary approach. Solar physicists, electrical engineers, radio astronomers, and materials experts began to collaborate more closely. The 3i Atlas phenomenon required combining knowledge that normally did not cross. Models developed to explain its emissions are now being applied in other fields, from solar storm prediction to designing satellites more resistant to radiation. But perhaps the deepest effect was philosophical. Humanity once again found itself facing something that seemed to border on the impossible. An unknown object from another stellar system sending detectable signals toward Earth. During the first days, doubt spread. What if it was something more? That question was not naive. It reflected the natural curiosity that has always driven science. However, when observations demonstrated that the phenomenon was natural, amazement did not disappear. On the contrary, it grew larger. The 3i Atlas did not need to be a ship or a transmitter to awaken the world's imagination. Its interaction with the sun was enough to remind us that the universe can produce invisible harmonies without any intention, only with the laws that govern it. While the object continues moving away, radio telescopes still track it, although its signals fade slowly. The last records obtained by FAST in China and Green Bank in the United States show that pulses are now irregular, weaker, like the last echoes of a cosmic conversation fading with distance. Some researchers describe this phase as the farewell of Atlas. Future studies will focus on measuring residual effects its passage left on solar wind. A slight disturbance has been detected in solar plasma density in the region it transited, suggesting the 3i Atlas acted as an electromagnetic catalyst. Understanding these effects could help explain how interstellar objects influence interplanetary medium dynamics, even after moving away. It is also expected that models developed to analyze 3i Atlas waves will serve to interpret emissions from exoplanets. Until now, astronomers have detected magnetic fields in some distant worlds through indirect observations, but direct confirmation remains a challenge. Methods perfected during the 3i Atlas study, especially correlation between radiation, stellar wind, and rotation, could be applied to those systems, allowing for the first-time measurement of a planet's magnetosphere outside the solar system. The 3i Atlas legacy also has implications for the search for life. Although its signals turned out natural, they demonstrated that the universe can produce regular and coherent patterns without need for intelligence. This forces extraterrestrial life search programs to refine their criteria. Truly artificial signals will have to be distinguished not only by frequency or repetition, but by mathematical or informative structures impossible to replicate through spontaneous physical processes. In a way, the 3i Atlas taught scientists to be more rigorous, but also more sensitive to cosmos nuances. The emotional aspect of the discovery cannot be ignored either. In the years that followed, documentaries, books, and exhibitions showed the 3i Atlas story as an example of observation power and collaboration. Graphs of its pulses converted to sound were played in science museums around the world. Listening to the object's voice, that deep and constant rhythm evoked a sense of connection with the universe that went beyond data. For millions of people, The three-eye atlas represented a metaphor for human curiosity, an unknown visitor that without intending to, made humanity look again toward the stars. Today scientists estimate that the object will reach the outer edge of the heliosphere in the coming decades. When it does, its interactions with solar wind will cease completely and its signal will disappear. However, its study already changed science forever. Every radio telescope pointing to the sky will carry with it the lessons learned, that even a silent body can emit music when sunlight touches it. That each interstellar visitor is a learning opportunity and that curiosity accompanied by method always leads to discovery. Perhaps in a not-too-distant future another signal will emerge from the depths of space. Maybe another interstellar object will cross our system and awaken the same question everyone asked that first night. Is the universe talking to us? When that happens, humanity will be ready to listen with better instruments, with more knowledge and above all with the same fascination that the three-eye atlas taught us to feel. The cosmos, although it does not speak with words, always responds to those who know how to observe it.